1. Do you agree?
Yes.
That's what we will have. Why? Because we have got an internal hinge over here. We have to respect the other boundary conditions of the member. Okay? It's only the quantity of interest, okay, that we are removing and then moving. We are removing the ability to resist that quantity, and then we are moving it up by unit displacement. So this is for RA. So everything is known. Okay. So in the exam you will be required to draw it, and by drawing inference line doesn't mean that you have to qualitatively draw it. You have to quantitatively draw it, and quantitatively how? By using Muller and Breslau principle. You can also do the hardcore first principle, which means that you actually place the unit load and then start moving it over here. Okay, but so keep on moving it until you reach E, and you will keep on finding the value. Now let us do a sense check on this, okay, whether this makes sense or not. So if we have a unit load in this, what does this tell us? That if we have a unit load in this area, in area between A and B, it's only then that RA would be active. As it moves to the other side, what will happen? This will be inactive. And if we see, like if we make a sense check on it, so it's true that if it is over here, then this is just like a link. And this is not going to take any load. Okay? You can only have load applied when it is over here, when you place the load on this link. So then you can have some load getting transferred. When it comes over here, then this is just a redundant member. Whether its presence is insignificant then. It doesn't contribute anything to your structure analysis. So this influence line also, so in the next class we'll be doing the application of influence line, and it tells us actually, it's not only that the movement of unit load, okay, on the member. It's not only as simple as that. It gives us some other interesting structural insights also. Yeah, and that is that if you that what will happen to your quantity of interest when you have loads applied in different places. Okay, so for example, if you are a structural engineer and you want to place a column, it's all a static member, but you have got the choice to place it in certain place. Okay, and there is one place, one location where you have you don't want the load to be placed. Like I can give you a practical example. Normally, in the case of facade, yeah, in the case of facade of a multi-story building, what happens is that you don't want the load directly to be coming onto the facade, because facade has got normally glass, and the glass can't take any load, isn't it? So you have to place, so if you have got a load bearing member, you have to place it in that particular location where it doesn't transfer any load to your glass, because glass will shut into pieces, isn't it? Yeah, if you, so I mean, if there is a facade over here, imagine, if there is a facade over here, okay, so this is actually, for example, this is it's a beam which is over here, okay. Imagine this room, and in this room we have got a beam over here. Or, okay, imagine this one. This is, for example, this is our facade. That is our facade, and this beam is in this direction, okay? And we have got, so we provide a pin over there, okay? A pin over there, and we have, and there is a column load which is coming somewhere over here, okay? A column load is coming over here. So we have got a choice either to place it over here or place it over there. But over here we have got facade. So the facade will start taking the load, and which we don't want. So we place it internally. Okay, so that the load doesn't get transferred. So I mean, like, so that sort of insight also you get from influence lines diagram. Do you understand my point?
Yes.
Yeah, it's making sense. Yeah. So this is for RA. Yes, it does make sense structure analysis wise. Why? Because if we place the load in this location, yes, this link will become active and it will start transferring the load to the point A. But if you keep on moving it and you place it anywhere in the other location, then this place won't be loaded. Okay, so that is something which we can we can do. Another thing is, like, normally the facade, we overhang it from the top. Okay, these are normally overhung from the top. So I mean, but that's different thing. So so that is one thing. Now RB. No, I should RC. It should be RC and RE. Okay, RC and RE. Now let's do RC. What happens in the case of RC? We have a okay, so now RC, okay, so there is a pin support or there is a roller support. Normally I told you it's insignificant whether you have got pin or roller. Okay, why in this condition when you have a vertical load coming? Yes, make sure that at least you have got one pin at least so that it doesn't roll over. Okay, your beam is stable. But if you have more than one pins, it doesn't matter really, because we very rarely have inclined oblique load. Now in the case of RC, what should we do? How should we draw our RC? RC is moving. Okay, so remove the ability to resist the reaction, which is this seam support. You omit that, and then you move it by unity. So how should we move it by unity? So the best thing is that first of all, let us allocate those points which are not going to move. Okay, so we have this point, it should stay over here because it's a support. Okay, so other kinematic conditions, these are the supports are sort of a kinematic conditions. So other conditions must be complied. Okay, so we have this one will not move. We will have this one which can not move. We have got this one which can move either up or down. Okay, but if we move our reaction, so we come over here and this is unity. Yes, so what will happen? We will have it something like this. Because there is a link over here. Okay, so we'll move it something like this. Please note that we are doing determinate structure and your inference lines must be linear. Okay, don't draw some nasty curves. This is not going to be curved, it's going to be linear. Your inference line is going to be linear. We had a discussion on this, and so everything is going to be linear.
So why is there a bend at C?
Why is there at C?
Yes, yes.
I mean, we have removed this support.
So this is a support, but from B to E, it is the same member, right?
From B to E. Okay, so now this is my question. Now, is this correct or not? I've drawn this. Okay, and now we have moved it like this. Now, is this correct or not? That's my question from you. It is correct. Okay, so please look into it carefully. Is this correct or not? We have applied a load in this direction. Okay, and this has moved. Is it satisfying all the kinematic conditions? What is the kinematic condition? First of all, one thing is that all your supports, okay, it shouldn't be displaced. So that is satisfied. This can move up and down, so it can move up and down. Can there be another point which can move up and down? There can't be another point which can move up and down. Can there be another point which can rotate?
So there are two pins in the center, so there are 2 points there.
Which 2 pins are there in the center?
B is hinge and C is pin support, so there are 2 pins.
No, but pin support means that it's just like this. It's not, this is an external pin. There is a difference between external pin and internal pin. External pin means that it can rotate like, it can go like seesaw. Internal pin means that you are releasing the moment and it moves like this. The external pin doesn't. You mean if we have a simply supported beam, you mean that this can move. We have a simply supported beam. So what does this simply supported beam tell us? That it allows movement. It's like a knife edge and it allows movement. Okay, but if I put a pin over here, that means that would allow this one to rotate with respect to this one, relative to this one. So what is going on in this one? This is a very common solution given to me by many students in the exam. That's why I'm writing this. What do you think? That is this correct or not correct? Look, guys, that gentleman pointed out very rightly. He gave you the hint, you are still saying that it is correct. How can this be correct? Why are we having a rotation over here? Is this a pin which can allow rotation? This is an external. I told you that this is a knife edge. So this is wrong.
But we have removed our.
We have removed this, but we are not introducing any pin over there. This is a straight member. If I put this thing over here, that means I'm putting a link over there, an internal pin over there. This is not, it is a knife edge support, okay? This is not, this member is straight. This is not a link. Do you understand my point or not? In this member, how many links are there? What do we mean by links? Like links are like chain. Okay, in chain, you have done in survey, you have done the chainage. So that chain is made up of lots of links, isn't it? In this member, how many links are there? There is one link. So how can you introduce another link? According to this, there are two links. So this 1, 2 and 3 members are actually acting like a link. In the given question, you have got 2 links. So how can you have a internal hinge introduced over here? That's what I'm saying, that there is a difference between the support external hinge, which is a knife edge support. You have just placed this support over here. In this case, you have released the moment between the 2 members. So it can rotate now. Do you understand my point or not? Any question about this one? Any question? Do you understand this is wrong? Those people who don't understand, tell me. They still have confusion about this one.
So, when we have the beam, so that is a member, but when we are drawing the influence line, that is a reaction line, that is not a member. So, can it bend?
No, it can't bend. Why can it? It's not going to bend. If you start bending something, that means you are making it curve. That's what I'm saying, guys. Look. Look at this thing. If I bend this, it becomes curved. And if I move it, it is straight. It's not going to bend. Because we are drawing it for determinate structure. We are drawing this influence line for a determinate structure. It's never going to bend. So, you just follow, because you have released one support, so it will automatically act, it will be a straight line, because it's a determinate structure. So, it will always be. If it bends, then that means it's an indeterminate structure.
Yes, sir.
So, this one is your, so it can't bend over here. And you can't release your support over here. So how is this going to be?
In diagram.
Okay, so we will have it again 1 over here, but and this will again go like this, but it will become, this is the only place where it can bend. It's not bending, it's actually zero movement, so it can rotate with respect to the other member. Is that okay or not? This is going to be a straight member because this is all straight member. There is no internal hinge. So this is going to be 1. You can find out what is this one. So this is 1 by 12. So this one is 1 by 12 is equal to y by 6. So y is equal to 0.5. This is 0.5. When you are asked to draw inference line diagrams, you have to work out all these ordinates, okay? Everything must be known. Okay, so you have to draw it quantitatively. And what is this? This is going to be 1.5. And this is going to be 0.5. Is that okay? Sorry? Just do similarity of triangle. 1.5 divided by, sorry, this one divided by 18 is equal to this one divided by 12. So do y1 divided by 18 is equal to 1 divided by 12. Is equal to 3 by 2. Is it not clear? Huh? I'm just doing similarity of triangle because it's linear. That's why. Yes.
So can you do a sense check on this?
A sense check. Okay, let's do a sense check. Now, imagine we have this thing moving along. Okay. So whenever it is over here, okay, the load is always the load will always be distributed between this one and that one. Agree? Agree?
Yes.
So whenever it is over here, what will happen? This thing will go like this. Okay, so so as we move along this C will have some reaction. Agree? When it crosses C, still then the load will be distributed between this one and that one, and still it would have reaction. So yes, we will have some reaction over here it will always have some finite reaction, regardless of where your position is, whether it's this place or that place.
Sir, from A to B there is a link, so the load should not only distribute on there.
Where we have got a link, yes?
At point B.
Yeah?
If the load is moving from point A to B,
Okay.
so the load be only distributed to A.
We distribute, if the load is between A and B, so load will be taken by A and it's not good. I mean, if you have a pin like this, is it possible that the load is always taken? You need another support, isn't it? So where is that other support going to come from? when you are standing over here, okay? When you are standing over here, so the load will not be, this is not a support. This is just a chain, a link. Imagine you are standing on a chain, okay, and the chain is embedded between, supported between two walls, okay. So regardless, wherever you are on the chain, the links don't take. So it's like a cord, and the load will be getting transferred to your support. So that's what I'm saying, that the load will always go there, and some portion you will see will go there also in E. But when you have, C will always be active, and that's what is said over here. If you want to do further check, as I told you, you can place the load over here, find the reactions, then place the load over here, find the reactions, place the load over here, find the reactions, and you will see that this one, and that's what's going to be your assignment, that you have to do it to a first principle and Muller and Breslau principle. Okay, so that's going to be your. Okay, so this is okay. So that's okay. Is that okay? Okay, now. Okay, so this is for R. This one was for RA. This one is for RC. Then we have RE. Again, RE has got this one. This one must be 0, and you have to move this one. Okay, this one can move in this direction. Yes. So remove the ability to resist reaction from E, and that will come over here. Now, so we must join this by a straight line. Please remember, don't break the member or bend it, and it will be straight going, and then it will become like this. Okay, so this is one. This is 1. You can easily find out 1 by 12. This is 1.5. This is 0.5. Yeah, this is 0.5. Yeah. So this will be 0.5. And similarly, you can find out this one, because if you know this one similarity, you know this one, and I think so. This one should also be 0.5. You have to work it out in exam. Please, I'm saying it again and again. Okay, don't just leave it blank. I'll mark you down if you do that. Okay, so you have to find all these ordinates. Okay, so is that okay? This is for RE. Yes, ask me. Yes.
Both C and A are not moving.
Sorry, speak up, please.
C और A दोनों moving कर रहे हैं तो B.
C or A, there is a pin over there.
But both of the members that.
Both C and A, both points are not moving, but they are like seesaw. So if you move this up, obviously this will come down, isn't it? No, why not? Imagine this is a pivot. Yeah, this is a pivot. It's like a, okay, and you sit over here. What will happen? You sit over here, what will happen? And this is a pivot. This is a pivot, and you sit over here, the seesaw will become like this, isn't it? Huh? Or not? Because this can move up and down. Are you getting it?
हमने E से हटाया लोड मतलब रेजिस्टेंस
Yes, when you get direct
But C is not moving, sir.
No, but C is not moving. C is not moving. C is static.
The C से straight line ही होगी.
C से straight line होगी. If C, देखिए,
Sir, the bend आ रही है.
if you make it a straight line from C, then that means you have to break this over here. How can you break it? I told you that you can't break it. That means that you will have to break it, isn't it? If this becomes exactly straight like this and then 0. So you have to break it. Then this member won't be intact. Do you understand my point? Or no? Because, so that's not allowed.
For example, if you take a load between B and C,
B and C, yes.
all the load is taken by C and E. The support is C and E. The load is not moving. The load is not crossing the internal E towards the left.
If we take this, sorry, say it again. Excuse me.
So if you take a load between B and C, somewhere anywhere.
If we take the load if the load position is between B and C, yes.
So all the load is taken by the support C and E.
Support C and E, yes. That's what you get from here.
So, but if we take it from A to B, why is the load being transferred from the hinge through the hinge?
Okay, yes. Look, what happens is, excuse me,
Yes, sir.
we have got this problem, okay? Yes, we have got if we place the load between, you are saying over here, if we have got the load placed over here, which is, yes, so you are saying why is the load taken, this is, why is the load taken by these two supports, yeah, why is it not going there? Because what will happen, this will bend like this, and this is just a link. So if you put the load over here, obviously these two are restraining this curve, isn't it? This one, this is just a link, so it is not taking anything.
But in the case if we take the load between A and the internal hinge,
If we take the load, now let's do this one. If we take the load between in this location, then what happens? We have, look, this hinge can transfer shear, yes? So some load will go there, some load will go there, yes? And then this load, equal load will become opposite. So this equal load will cause again this thing to move like this. So therefore, this will take the load. You understand my point? But it's very good that you make this sort of sense check, because that will enhance your structural analysis understanding. Okay, so like how this load is actually, so that's what the beauty of influence line. It tells you, like, you know, how structure is behaving. Yes. Okay, shall we move forward? Is that clear? Yes. Okay. Now, moment at D. Moment at D. First of all, again, let us establish those points which are not going to move, okay? And this time they are all the supports. isn't it? So you have this support which is not going to move, you have this support which is not going to move, and you have this support. This hinge can move up or down. Yes? Now, what happens in the case of moment? We said that remove the ability to resist the moment at point D. So removing the resistance means that to install a pin. Is this pin, okay? So we have to place that pin over here. Agree? Now, once you place this pin over here, now either you move it up or down, but you have to make your judgment. I told you that normally it's better that you draw it on the tension side. Okay? So, if I have to draw it on the tension side, what should I do? Should I draw it at the top or bottom? That's the... So if I put over here, I've got these moments. Okay, I've got these moments applied. These moments, what does it tell us? If I've got a moment like this applied, then that means that where is our tension? At the bottom. Yeah? And if I got this one, so tension is at the bottom. So I should better move it down. Okay, so if I move it down, I have shown you over here what happens normally in most of the cases. In most of the cases, when this is moving, what happens? Your tension is like this, isn't it? So now what should we do? I told you that you have to make use of your engineering judgment that where you should move it. Okay? In this case, in most of the time, when you have load moving in this direction, yeah, most of the time the tension is up, isn't it?
No, sir, it is equal, sir. For 12 feet it will be up, and for the next 12 feet it will be down.
No, but yes, for this one it will be up.
And for the next 12 it will be down.
Yeah, it will be down. So that means that when the load is over here, okay, then you should have tension
On the upper.
over here. Agree? And when the load is over here, you should have the tension downward. So this assumption, so if I put this hinge down, then it makes sense. Does it, so do you agree? Yeah? Okay, let me repeat what I'm saying, okay? We discussed, and I told you that it's always helpful to draw the moment diagram on the tension side, okay? So, why? Because then you can appreciate how the elastic curve, which is this one, how the actual bend profile and the bending moment, they are corresponding with each other. Okay? And so, from this question we can see that as we move our load, when the load enters this point, so when the load enters this point, what happens is this thing will be pushed up. It will lift off. CE this span will lift off, isn't it? It will move up. So when we are moving it along this point, then our moment should be positive or negative. I mean, should it be above or below? When we are moving it over here. So because your elastic curve is up, so it should be above. Okay? And when you come within this span, then this is just a simply supported beam sort of thing. Okay? The other point, they are doing nothing. All the rest of the member becomes redundant. So when you move it inside, then your tension, so it is so the tension is at the bottom, okay, at the bottom fiber. So that means that we should have it over here. Okay, so if we do it over here, this thing will automatically be adjusted. So now, what did we say in the previous class? That so if I put it like this, that means that I've got a link over here, I've got another link over here. Isn't it? I've got two links. So one link is over here. So this will, sorry, this will go down. Then it should go like this.
Yes.
And it makes sense with our structure analysis. Yes, so automatically the sense check is satisfied. Yes, so now we are saying theta 1, theta 2. Okay, so theta 1 plus theta 2 must be equal to 1. That is what we discussed previously. Yes. And what is theta 1? Imagine this is h1. So h1 by 6. Okay, so this is so what do we have? H1 by 6 must be equal to H1 by 6, which is, so that's what we would have. H1 by 6 plus H1 by 6 is equal to 1. So 2H1 by 6 is equal to 1 and H1 is equal to 3. So this one will come out to be 3. Is that okay? Yes? Now if this is 3, 3 by this one is equal to H2 by 6. So this one will also be 3. So that's it. Is that okay?
That unity thing, what it can.
Sorry, speak up please.
That unity thing that you will move it.
What unity thing?
Sir, अभी तक हम unit move कराते हैं.
So I'm saying that when you move it over here, the moment has got the corresponding deformation in terms of theta, isn't it? It's a rotation. Moment will give you rotation. So that rotation must be equal to 1. So this rotation, theta 1 plus theta 2 must be equal to 1. That is for moment, isn't it? We did it in last class, didn't we? This rotation, theta 1 plus theta 2, this must add up to 1. You must rotate these two in such a way that the sum of these is equal to 1. Isn't it?
That this one is.
This is that unity. In the case of moment, you have to make sure that this thing is 1. For the reaction, we had a displacement equal to 1 in the force direction. In this case, you have these rotations, which must be equal to 1 in the case of moments. Yes?
Yes.
So, is that okay?
Yes, sir.
Any question? Okay, now let us do Should I rub off the top one, yeah?
Yes.
We have done it. Let me, this is all clear. So for shear, now we have shear at D. Okay, shear at D. Guys who are writing, you just continue. Okay, you just draw it under the moment. You can draw this diagram because I don't have enough space. That's why. Okay, so in case of shear, we discussed that we have to introduce shear release. Okay, and the shear release should allow sliding. Yes, so what will happen? We will have, this is our VD. So again, establish those points which are not going to move. So again, this one is not going to move, this one is not going to move, and this one is not going to move. This can move up and down. Okay, and we introduce shear. So in case of shear, I told you that our sign convention is that. Okay, that's what our sign convention. Yes or no? So if we introduce the shear release over here, what will happen? We should have one end moving down, another one moving up. So if this is moving down, and the overall shear is 1. Is that okay?
Yes, sir.
So I've introduced that release. This one moves down, this one moves up. And we know that shear always has got two values. One towards the left and one towards the right. Okay? That's why we have it. So this one moves down, this one moves up. Okay, so then what do you think? You think that whether I've drawn my influence line diagram linear. So check, yes, that's linear. Another thing is that all the kinematic boundary conditions, they are satisfied. Yes, this one click, this one click, this one. Yes, all three of them are satisfied. It is moving, the internal hinge, it is moving up. Yes, that's satisfied. Now in case of shear, I told you that please, because we are just releasing shear, so this, the slope of this one must be equal to the slope of this one. Yeah, so this, whatever I called it previously, I don't know, but this alpha, if this is alpha, this one is also alpha, because these two slopes, you're not changing. If you change the slope, that means you're releasing the moment also. Yes, which we are not. Release only one thing at a time. Yeah, so we have released the shear and we haven't released the moment. Previously we had released the moment. Okay, so that is what we have now. Once it moves like this, now and this whole thing is 1. The whole shear is 1. Now we have to work out our ordinates. So what is our ordinate? This one is like I call it H1. You can call it anything, H1, H2. So H1 divided by 6 is equal to H2 divided by 6. Okay, so H1 divided by 6 and H2 divided by 6, which tells me that H1 is equal to H2, and that means that, and another equation is H1 plus H2 is equal to 1. Yes, so we will have H1 is equal to 0.5 and H2 is equal to 0.5. So now we have this 1.5, this 1.5. Yes? Now, if this is 0.5, this one is also 0.5. So everything is known now. Any question? Is that okay?
Yes.
Shall I rub it off then? Yes?
यार कोई नहीं पता कैसा सही बात है भाई 2 to 4 क्लास सही बात है ना कोई नहीं है अभी अनाउंस नहीं हुआ ना 12:30 बजे प्रिंसिपल अनाउंस करेगा मेरा मैच आई देखी क्या है खेलेगा
Okay. Now we'll discuss inference lines for fixed support. Okay. So far we have discussed roller supports, hinge supports.
Yes.
Okay. These are all classed as pinch supports. Okay. External pinch, external supports. Now we'll discuss fixed supports. What will happen if I have a fixed ended beam and let me
मैं कहाँ ही जा सकता टाइगर 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 कितने तक टाइगर जमीन
टाइगर भी पूरा है
हाँ आ रहे
Now this is okay. Now in fixed supports, we can again use Muller and Breslau principle. Okay, and but we have to use it a bit judiciously. Now, what do I mean? For example, one thing which we must make sure in the case of fixed support, that is that support shouldn't rotate. Okay? In the case of pinned support, when we move our structure, so for example, if we had a pinned support, a simply supported beam, yeah, and if we moved it up, for example, in case of finding out reactions, okay, if it didn't matter whether this was in whatever the inclination of this member was. Why? Because the kinematics of this pin connection, this allows any rotation. Okay? Now if we have, I want to have your attention please, okay? If we have a fixed connection, so and I want to find out reaction, so can I have something like this? Or again, can I have an inference line something like this? Or can I have an inference line something like this in the case of fixed connection? What do you think? What is upper one telling me?
There is no rotation with the fixed.
But I told you a few minutes back that you can never have a curved structure in case of determinant. So this is wrong straight away. So if you draw something like this, that means big fat zero. Okay? Yes. So you have so this one can never be your influence line for a determinate structure. What happens if what about this one? No, but this is linear. This is linear. So, is there anything wrong? And if there is, what is that thing?
It's not coming.
जी
ये वाला जो
ये वाला
है
एंड जो है
ये
Right.
हाँ
सर ये ऊपर लाइक
Zero पे आएगा.
ये क्यों इतना हो गया? Yes. Why? Because what is this telling you? देखिए, this one is telling you that this is making, initially it was 90 degrees. Now this inclination has changed, it has reduced. But I told you that according to Muller and Breslau principle, you are not going to change the kinematics of your, this, when I say kinematics, everything related to the elastic curve, to the deformed profile. Okay? So the deformed profile, you shouldn't change. Previously, we did this sort of thing and we were not concerned about this angle because pin allowed any sort of rotation. Yes? In this case, this thing is not allowed. So what you can have is, yes, exactly. So what you can have is, we can have it, the only way we can have it, we can draw our reaction is a straight line. You can just move it and the whole thing should move up. Is that okay or not? Are you getting this?
Yes.
Yeah, making sense. So this is I mean that's just a small understanding which you must have in order to draw your influence line for fixed and fixed supports. Okay. So now what happens is, so now let's draw RA. RA is RA, which is this is my MA. Okay, I would have my MB and MC, and then we'll make a sense check on it. Where should our moments and shear lie? Okay, but first of all, RA is easy. Whether you want to draw it through hardcore first principle, still it's okay. I mean, I put my unit load over here. No matter where it is, my reaction is going to be 1. Isn't it? And using Muller and Breslau principle, if I have to move the whole thing up. So both sense checks and everything agrees. Agrees? Yes. So that means that we will have a straight line, which is like this. Okay? Is that okay? So this one is 1. And this one we call R A. Right? Yes. Okay. Now we have moment at A. Now what will happen to our moment at A? Let us draw first of all this one. So the free end, the kinematic condition of the free end is that it can move anywhere. So I mean you can put it anywhere. It can move in this direction or in this direction, doesn't matter. So if I move it up, now what should I do in case of moment? In moment, how do we introduce internal hinge? Okay, so the internal hinge must be introduced. Now, if I introduce internal hinge over here, can I introduce internal hinge below or above? Why no? The support cannot, if I introduce it as in previous case above or below, that means that I am moving my support, which can't move. So this is at the support which I am introducing my internal hinge. So it has to stay at the support. Now, in the case of internal hinge, we had 2 theta's, remember? Theta 1 and theta 2. But that was for the case when we had 2 members on both sides. Now we have only 1 member on one side. So that is going to be, that rotation is going to be 1. Okay, it's not the theta 1 plus theta 2 business. Okay, it's only theta 1 is equal to 1. You agree? Okay, so now which direction should I move? Okay, now if my load is moving in this direction, my moment is, no, it's not clockwise. I mean, like, where is the tension? Tension is, so I should draw my moment at the upper side. So, in other words, if I draw something like this, this is 1 and this is 20. Okay? 20, isn't it? 10 and 20. So this is 1, this is 20. Then we would have now MB. In the case of MB, what should we do? This one can't move. This can move up and down. What do you think? We are not going to violate any kinematic condition, okay?
You are finding MB or BB?
MB.
MB.
MB. This is our MA. This is MA. MB. What should I do? Sorry?
Provide a hinge and
Okay, we provide a hinge, but should the hinge be above, below, or at the same point? Okay, so should we provide it above? Okay, I provided it over here. Now what should I do? If I provide it above, you mean I join it like this?
No, sir.
If I join it, I violate this thing.
Center.
So we put it. So exactly. So we can't have it above or below. We can have it only. Over here. And
sir, we can go up or down.
now we can put our hinge over here and move the member above or below. Above. Why? Because tension is always above. Isn't it? So we will have tension above. So this will be.
No, sir, the tension can be down. When the load is moving from fixed support towards B, from A to B, the tension will be up. Upper side.
If it is moving like this will always be bent.
Sir, after then.
Wherever, regardless wherever it is, tension is always up, isn't it? It's fixed. Yes? So, this is 1. And this is my 10. Is that okay? This is 1 radian, okay? This is, just say tangent theta is equal to 1. Yeah, so this is radian. Okay, now shear.
Sir, you have said something about violating a condition. What was that?
Over here I said
Yes.
that if I put my hinge above or below, what will happen is that I'll have to join this thing with this one, and this is my fixed handle. So obviously I am rotating this, okay, which is not allowed in case of fixed. If this was a pin, yes, that was allowed, but in fixed it's not allowed. So you have to appreciate that. Okay? That this thing is the support conditions are not violated. Yes. Now the last one is shear. Now the shear case, again, it's the same situation. We yes. So what will happen? I put that thing.
Yes, sir, straight and then up and
What do you mean? Sorry, straight. So okay. First of all, let us establish our kinematic condition. This is going to be 0, isn't it? And this can move up and down. So if I put it over here now, what should I do? ऊपर नीचे What should happen over here?
Straight line.
it should be straight on 0.
Straight line where? Above, below, at 0. Yes. So this will be at 0 because if I move this up or below, that means that I'm moving the support, which is not allowed. So this will come to 0. It is over here, and now this can come down. Yes.
Then it will go up or down.
This one is not doing anything, and this one will bring it down. Now it can come down, can't it? Because this is a free hand, you can move it down. So this one is so you can yourself imagine that if your unit load is over here, yes, the shear force is 0, isn't it? When your load is over here, you have got reaction over here and load is over here. So up till here, the shear force is always 0, isn't it? The moment it crosses this point, then what happens? You have a shear force introduced, and that is, so if it is like this, you will have it in this direction. So this is opposite to this one. Yes? So that's why you get negative. Sorry?
So the second half was supposed to be on the positive side.
Why?
So we use the same convention in the previous question.
No, for shear, we always use this one. In the previous case, we moved this one up and this one down.
No, sir, we moved left side downward and right side upward.
In the case of, was that for shear?
Yes.
Left side downward, right side.
Show me in the shear case, what did we do? No, in the shear case, I moved this one down and this one up. So why are you saying that I did upside down? I did other way.
Left side downward and right side.
This one moving down, this one moving up.
Yes,
Sorry?
the left side down and right side up, sir. Left side down and
Right side. We have clockwise shear.
Yes.
We have got this one and this one. Okay? That's what we have. Yes. So in this case, we have.
Positive.
Yes, you are right. This is positive. Yes, I agree with you. Yes, this is mine. We follow this one. Thank you very much. Sir. Thank you. This one is moving up. Yes. So this one up, this one down. This is our center dimension for shear. Yes. And this is falling up. Okay. So now I'll give you some. Are you going to submit your assignments? Okay. So that's it for today. Any question? No? Okay. Yeah. Can you switch it off? Thank you very much.